In 1995, as Japan reeled from the devastating Kobe earthquake that claimed over 6,400 lives, engineers watched nervously as the unfinished towers of the Akashi Kaikyo Bridge swayed violently. The world's most ambitious bridge project was being tested by nature before it was even complete. The towers moved permanently, expanding the bridge's length by almost 3 feet overnight. Yet the structure held. How did Japanese engineers build a 12,831-foot suspension bridge that could flex with one of history's most powerful earthquakes and remain standing? The answer lies in a set of innovations that defied conventional wisdom, turning what seemed impossible into reality. Before we dive into this incredible story, make sure to hit that like button and subscribe to our channel for more amazing stories about the world's most extreme builds. Don't forget to turn on notifications so you never miss an upload. Building the world's longest suspension bridge is difficult enough, but placing it in Japan created a challenge that many engineers considered impossible. Japan sits on the Pacific Ring of Fire, where 4 tectonic plates meet, causing more than 1,500 earthquakes every year. This seismic reality meant that connecting Kobe and Awaji Island across the 4-kilometer Akashi Strait would require engineering solutions that simply didn't exist at the time. The need for this connection was clear. Residents and businesses relied on ferry service that took 2 hours to cross waters that could be driven in just 5 minutes, if a bridge existed. The economic benefits came with serious questions. Could any structure withstand the extreme forces that had destroyed bridges in similar conditions around the world? Engineering history offered sobering lessons. The 1940 Tacoma Narrows Bridge collapsed from relatively mild winds compared to Akashi Strait's fury. Similarly, the 1964 Alaska earthquake devastated multiple bridges with forces Japan regularly experiences, like structural stress tests that most designs repeatedly failed. The Akashi Strait was nature's gauntlet of engineering challenges. Typhoons hammered the region with winds reaching 180 miles per hour, like a relentless battering ram testing any structure's limits. Ocean currents flowed at speeds of up to 10 knots, while the seafloor consisted of unstable silt rather than solid bedrock. These combined forces created a perfect storm of obstacles that seemed insurmountable. For Japan in the post-World War II era, this project represented more than infrastructure. It symbolized technological rebirth and determination to overcome natural limitations. Public support intensified after the 1955 Akashi Strait ferry disaster, when 2 vessels collided in fog, claiming 168 lives in the churning waters below. When Japanese officials proposed the bridge in the 1960s, the global engineering community expressed profound skepticism. American bridge expert David Steinman stated that no bridge could survive the combination of seismic activity, powerful winds, and strong currents present in the Akashi Strait. Undeterred, in 1988, the Japanese government assembled an elite team led by Takashi Hayashida of the Honshu Shikoku Bridge Authority. They faced a clear mission requiring 7 integrated revolutionary technologies, never before combined in a single structure. Conventional bridge design principles would fail under these conditions. The team needed flexible towers that could move with earthquake forces rather than resist them, a deck design redirecting typhoon winds, foundation systems securing the structure in poor soil conditions, and cables allowing controlled movement during seismic events. The project demanded reimagining fundamental principles of suspension bridge function in extreme conditions. This meant developing systems where earthquake forces would be absorbed rather than resisted, where wind would pass through the structure, and where foundations could remain stable despite unstable ground beneath them. Traditional bridges are built to resist forces, but the Akashi Kaikyo Bridge was designed to move with them. In a region where earthquakes and typhoons regularly test human structures, engineers realized that fighting against these forces would lead to failure. The solution required 7 revolutionary technologies working together to create a bridge that could absorb, redirect, and adapt to some of the most powerful forces on Earth. Want to learn more about how engineers solve impossible challenges around the world? Check out our related videos linked in the description below. The first breakthrough came in the form of flexible steel towers designed to sway with earthquake forces. Each tower stands 300 meters tall, higher than the Eiffel Tower, and was constructed from 30 individual sections. This flexibility represented a fundamental shift in engineering philosophy. Rather than building rigid structures that crack under pressure, engineers created towers that bend without breaking, dissipating seismic energy through controlled movement. To achieve this perfect balance, engineers developed an entirely new grade of steel with optimal tensile strength, ductility, and weight. The material supports massive loads while allowing precise movement during seismic events. This specialized steel became the backbone of the bridge's resilience. But the towers alone couldn't defy nature's fury. Inside each tower, engineers installed massive 10-ton pendulum dampeners, working like giant counterweight clocks that steady the structure during tremors. When an earthquake strikes and towers begin to sway, these pendulums move in the opposite direction, neutralizing destructive energy that would otherwise tear the bridge apart. The foundation challenge required anchoring in water 60 meters deep without solid bedrock. Engineers created massive caissons, enormous hollow structures that became each tower's foundation. Once positioned by 12 coordinating tugboats, workers filled these steel shells with 230,000 cubic meters of concrete, creating artificial islands stable during seismic events. The bridge's massive cables represent another engineering marvel, containing enough wire to circle the globe 7 times. Arranged in strategic bundles, these cables support the bridge deck while permitting the controlled movement essential during earthquakes, their dynamic properties resembling the flexibility found in martial arts. The bridge deck features an open box design modified for Japan's extreme conditions. Strategic grills allow typhoon-force winds to pass through rather than push against the structure. A massive steel beam below the roadway redirects wind upward through these grills, essentially allowing the bridge to breathe during storms. Computer modeling and wind tunnel testing with detailed 1/100th scale models allowed engineers to refine these innovations. The team subjected these models to simulated earthquakes and typhoons, measuring responses and improving performance. These tests confirmed the bridge could handle both seismic and weather extremes simultaneously, a crucial requirement in a region where typhoons and earthquakes sometimes occur together. The Akashi Kaikyo Bridge faced its ultimate test before it was even finished. On January 17, 1995, at 5:46 in the morning, the ground beneath Kobe began to shake violently. The Great Hanshin earthquake, as it would come to be known, unleashed a magnitude 7.3 shock that would test everything the engineer team had designed. In just 20 seconds, the earthquake devastated the region by surrounding the bridge. A catastrophic warning reshaped the area, claiming 6,434 lives, injuring 43,792 people, and leaving more than 200,000 buildings collapsed or severely damaged. As dawn broke over Kobe, fires raged across the city, elevated highways lay toppled, and thousands were trapped beneath the rubble. I watched the towers swinging back and forth like trees in a typhoon, recalled one worker who had been on the structure when the quake hit. My legs froze. I was certain we would all plunge into the strait below. Workers described gripping steel cables as the massive 300-meter tower swayed violently, praying the structure would hold. In the chaos, an unexpected discovery emerged that would forever change engineering designs. When engineers reached the site, they found something remarkable. The earthquake had physically moved the foundations of the towers. Precise measurements confirmed what seemed impossible. The towers were now approximately 3 feet further apart than before. The bridge had literally grown overnight. The engineering team faced an unprecedented situation. Years of planning, billions of yen, and countless work hours had gone into a design with specific dimensions. Now those dimensions had changed. Would they need to start over? Had the structural integrity been compromised? For 3 weeks, engineers conducted comprehensive assessments of every component. What they discovered validated their design philosophy while presenting new challenges to overcome. The bridge survived because it was designed to move. The flexible towers had swayed as intended, absorbing seismic energy rather than resisting it. The foundations, while shifted, remained secure. The bridge performed exactly as theorized during an earthquake. The extended length created engineering problems requiring immediate solutions. Where the original calculations specified exact cable tensions of 120 meganewtons, engineers now needed to recalculate the expanded span, adjusting both tension and angle of the massive supporting cables. Engineers adapted the design by modifying cable configurations, adjusting deck sections, and recalibrating dampening systems. The earthquake provided invaluable real-world data on the bridge's response to seismic forces, allowing engineers to identify successful elements in areas needing improvement. When the Akashi Kaikyo Bridge opened in 1998, it incorporated lessons learned directly from the earthquake. The completed bridge emerged stronger, more flexible, and better understood. The design principles validated by the Kobe earthquake now inform bridge construction throughout earthquake zones worldwide, an unexpected legacy of the terrible morning in 1995. Today, more than 2 decades after its completion, the Akashi Kaikyo Bridge stands as proof that human ingenuity can overcome even the most extreme natural challenges. The bridge has withstood numerous earthquakes and typhoons without a single structural failure since opening in 1998. What once seemed impossible became reality through innovative engineering. The impact extends beyond Japan as a beacon of human achievement. The flexible tower design, pendulum dampening systems, and wind-resistant innovations protect infrastructure worldwide. Engineers globally have adapted these technologies, creating safer structures that move with seismic forces. This legacy continues to inspire future generations of builders who look to this marvel as a testament to what we can achieve when technology and human determination unite. What do you think about the Akashi Kaikyo Bridge? Share your thoughts in the comments below. We'd love to hear your perspective on this engineering marvel. Enjoyed this video? Don't forget to like, subscribe, and share it with friends who love learning about incredible engineering feats. Your support helps us bring you more amazing content like this.